And the craziest part is Kubernetes orchestrates billions of containers every single week at Google alone. Billions! I mean, think about that scale for a second.
Okay, that is mind-boggling. But most of our listeners aren't running at Google scale. Why should a team with, say, a dozen microservices even care about the nitty-gritty of Kubernetes?
That's a great question, Priya. It's like understanding how your car engine works. You don't need to be a mechanic to drive, but when the check engine light comes on, knowing the basics can save you from a tow truck and a huge repair bill. With K8s, when deployments fail mysteriously or your app starts acting flaky, understanding the underlying mechanisms is crucial for debugging and preventing outages.
Okay, I'm with you. So ignorance isn't bliss when production is burning. What's the cost of not understanding this stuff?
Think about Netflix. They're constantly deploying new versions of their services. Imagine if a misconfigured deployment brought down their recommendation engine during peak hours. Millions of users would see generic content, subscriptions would be canceled, and the engineering team would be scrambling to fix it. A solid grasp of Kubernetes internals drastically reduces the blast radius of those kinds of failures. It's the difference between a minor inconvenience and a full-blown crisis.
All right, disaster averted. So let's dive in. Let's start with the fundamental building block, the pod. Everyone talks about them, but what actually is a pod in Kubernetes?
Think of a pod like a little apartment building. It's the smallest deployable unit in Kubernetes, and it can contain one or more containers that share resources like network and storage. The containers inside a pod are tightly coupled. They're designed to work together.
So why not just run everything in a single container? What's the advantage of grouping containers inside a pod?
Good question. Imagine you have a web application that needs a web server, like NGIX, and an application server, like a Python Flask app. You could cram both into one giant container, but that makes scaling and updates a nightmare. With pods, you can have separate containers for NGIX and Flask, and they can communicate with each other easily within the pod. Plus, if the Flask app crashes, NGIX can still serve static content, providing a more resilient user experience.
That makes sense. So it's about isolation and resilience. But what about resource allocation? How does Kubernetes manage the resources for each pod?
Each pod can have resource requests and limits defined for CPU and memory. The requests tell Kubernetes how much resources the pod needs to start, and the limits define the maximum amount of resources the pod can use. Kubernetes uses this information to schedule the pod on a node with enough available resources.
Okay, so Kubernetes is like a careful landlord, making sure each apartment building has enough power and water. But what happens when a pod needs more resources than it requested? Does it get throttled?
Exactly. If a pod exceeds its memory limit, Kubernetes will likely kill the container. If it exceeds its CPU limit, it might get throttled, which can slow down your application. That's why it's crucial to carefully size your pods and monitor their resource usage.
Makes sense. Now let's talk about scheduling. How does Kubernetes decide where to run a pod? It's not just randomly throwing them onto nodes, right?
Definitely not. The Kubernetes Scheduler is a sophisticated piece of software that takes into account various factors when deciding where to place a pod. Think of it like Uber assigning drivers to riders. It needs to consider factors like resource availability, node affinity, taints and tolerations, and even custom scheduling policies.
Node affinity and taints and tolerations sound complicated. Can you break that down?
Sure. Node affinity allows you to specify rules about which nodes a pod can run on. For example, you might want to run a pod on a node with a specific type of hardware, like a GPU for machine learning workloads. Taints and tolerations are the opposite. They allow you to mark nodes as unsuitable for certain pods unless the pod explicitly tolerates the taint.
So taints are like keep out signs on nodes?
Precisely. Imagine you have a dedicated node for running critical database workloads. You can taint that node so that only pods with a specific toleration can run on it, preventing other applications from accidentally consuming its resources.
That's a clever way to isolate workloads. What happens if a pod can't be scheduled anywhere because there aren't enough resources available?
The pod will remain in a pending state until the scheduler can find a suitable node. This is where things like autoscaling come into play. If you have autoscaling enabled, Kubernetes can automatically provision new nodes to accommodate the pending pods.
Okay, so the scheduler is constantly trying to balance the needs of the pods with the available resources. What about custom scheduling? How do those work?
Kubernetes allows you to create your own custom schedulers that can take into account even more specific factors, like cost optimization or energy efficiency. For example, you could write a scheduler that prioritizes running pods on nodes with lower electricity costs.
That's pretty advanced. Now let's move on to the heart of Kubernetes, the control plane. What exactly is the control plane and why is it so important?
The control plane is the brain of Kubernetes. It's a collection of components that manage the overall state of the cluster. Think of it like the air traffic control tower at an airport. It's responsible for making all the important decisions like scheduling pods, managing deployments, and handling service discovery.
So what are the key components of the control plane?
The main components are the kube-apiserver, etcd, kube-scheduler, kube-controller-manager, and cloud-controller-manager. The kube-apiserver is the front end of the control plane. It's the only component that you directly interact with when you're managing your cluster. etcd is a distributed key value store that stores the state of the cluster. The kube-scheduler we already talked about. The kube-controller-manager runs various controllers that are responsible for maintaining the desired state of the cluster.
Controllers. What do they control?
Everything. There are controllers for deployments, services, nodes, and more. For example, the deployment controller ensures that the desired number of pods for a deployment are always running. If a pod crashes, the deployment controller will automatically create a new one to replace it.
So the controllers are constantly monitoring the state of the cluster and taking action to keep it in the desired state. What about the cloud controller manager?
The Cloud Controller Manager is responsible for integrating Kubernetes with your cloud provider. It handles things like provisioning load balancers, creating storage volumes, and managing routes.
Got it. So the control plane is a complex system of interconnected components that work together to manage the cluster. What happens if the control plane fails?
That's the million-dollar question. If the control plane fails, you won't be able to deploy new applications, scale existing applications, or make any changes to your cluster. Existing applications will continue to run, but you won't be able to recover from failures. That's why it's crucial to have a highly available control plane with multiple replicas. Cloud providers like AWS, Google Cloud, and Azure offer managed Kubernetes services that handle the complexity of managing the control plane for you.
Okay, so a highly available control plane is non-negotiable for production environments. Here's where it gets interesting. A lot of engineers treat Kubernetes as a black box. They deploy YAML files and hope for the best, without really understanding what's going on under the hood. What's the biggest mistake you see people making?
The biggest mistake is not understanding the resource requirements of their applications. They often under-provision resources, leading to performance bottlenecks and instability, or they over-provision resources, wasting money and reducing the overall efficiency of the cluster. It's a delicate balancing act.
So it's not enough to just deploy your application to Kubernetes. You need to carefully monitor its resource usage and adjust the resource requests and limits accordingly. What's a practical way to do that?
Start with realistic load testing. Simulate real-world traffic to your application and monitor its CPU and memory usage. Use tools like Prometheus and Grafana to visualize the metrics and identify bottlenecks. Then adjust the resource requests and limits in your pod definitions based on the observed usage. Iterate and refine until you find the optimal balance between performance and cost.
Okay, so test, monitor, and adjust. Makes sense. What's another common pitfall?
Another common mistake is not understanding the importance of networking. Kubernetes networking can be complex, especially when you're dealing with multiple services and external traffic. People often struggle with things like service discovery, ingress controllers, and network policies.
Network policies can be a real headache. What's the key to mastering Kubernetes networking?
The key is to start with a solid understanding of the underlying networking concepts, like IP addresses, ports, and DNS. Then learn how Kubernetes uses these concepts to implement service discovery and routing. Experiment with different ingress controllers and network policies to understand how they work. And, again, monitor your network traffic to identify bottlenecks and security vulnerabilities.
So networking is another area where you need to get your hands dirty and experiment. What about security? Is that another common area where people make mistakes?
Absolutely. Security is often an afterthought in Kubernetes deployments. People often neglect things like role-based access control, or RBAC, pod security policies, and container image scanning. This can leave your cluster vulnerable to attacks.
So what are some basic security best practices for Kubernetes?
Implement RBAC to control who has access to your cluster and its resources. Use pod security policies to enforce security constraints on your pods. Scan your container images for vulnerabilities before deploying them. And regularly audit your cluster to identify